Let's talk about the hyperbola. We're going to start by talking about something that we learned earlier, which was the circle. And a circle had a shape that looked something like this. And with the circle, we had pretty much two characteristics. We had a center, which was located at HK, and we also had a radius. We sort of talked about the radius being in the x direction and the y direction. So we had an r sub x and an r sub y, and we said that the radius r sub x was equal to r sub y. And that was a circle. And the equation of the circle we obtained was this: x minus h squared plus y minus k squared equals r squared. Then we talked about the idea of taking r sub x and r sub y and making them unequal to each other. So maybe r sub x is bigger than r sub y. And that led us to the idea of an ellipse. And so for an ellipse, you still had a center point at h and k, but this time maybe r sub x was bigger and r sub y was smaller. And we said that r sub x in this case would be the major axis. Whichever one of these two, r sub x or r sub y, was bigger, that was the major axis. You also have vertices where r sub x meets the edge of the ellipse. But there is one more thing that we have, and that's a focal point. So an ellipse has a focal point on the major axis. Taking this conceptually and moving it to an equation, the equation for the ellipse is going to be x minus h squared over r sub x squared plus y minus k squared over r sub y squared equals 1. And we obtain this by taking the equation for the circle and just dividing it by r squared. So you divide every term by r squared, and then you differentiate the r under the x term as r sub x and the r under the y term as r sub y. There was a second equation that we also got with the ellipse, which referenced the focal point. We obtained that by using the Pythagorean theorem, and it became this: the focal point is equal to the square root of r sub x squared minus r sub y squared. So now there's one more shape we can derive. When we had a parabola, the original definition of a parabola was that you had a focal point and you had this thing called the directrix. And all of the points of the parabola, the green edge, were equal distance from the focal point and the directrix. So if you took this point right here, the distance from here to here is the same as the distance from there to there. And that's what sort of created the parabola. What if we took this directrix, this line, and we curled it, and we made a circle? So now we have a focal point, the green dot, we have a center right here, and this curve, this circle, that black circle that you see, imagine that's the directrix wrapped around as a circle. So as we get closer and closer to the directrix, this kind of like parabola shape that we have here, the ellipse, it gets more narrow. Just like when we go to the parabola, the closer we get to the directrix, it gets more narrow. See that? See how it gets narrow the closer we get? When we pass through to the directrix, to the other side, what happens to our parabola? It flips, right? It opens down instead of opening up. So let's look at this idea. What's going to happen as we get closer and closer to the circle directrix and pass through it? Flip. See that? Ellipse. Hyperbola, or a hyperbola. So the green edge that you see here is a hyperbola. So essentially what we're doing is we're taking the focal point that we just sort of talked about as a characteristic as of an ellipse, and we're going to move it through the vertex C, past the vertex C, to the other side of the vertex C. So we're going to talk about a hyperbola. And our hyperbola has a center point located at HK. It'll have a vertex here and another vertex here. And the difference is the focal point is outside of the vertex. So that means it opens towards the focal point like this and towards the focal point like this. There still is an r sub x, which is the distance from the center to the vertex. That's r sub x. And there's still an r sub y, but r sub y doesn't really touch anything. There's almost like a hidden ellipse in here. So what's the equation of a hyperbola? It looks like this. X minus h squared divided by r sub x squared. Hey, that looks familiar. Minus y sub k squared divided by r sub y squared equals 1. So it's the exact same formula that we had for the ellipse, except for instead of adding the two things, you subtract them. There's also an equation for the focal point, which is the square root of r sub x squared plus r sub y squared. And that's exactly the same as the equation for the focal point of an ellipse, except for instead of subtracting them, you're adding them. There's one more thing that we want to talk about. This hyperbola actually has an asymptote that goes like this, and another asymptote that goes through it like this. To find the equation or the slope of these asymptotes, what you would do is, it's actually not bad. You can use sort of triangles again, triangle trig. If you move that r sub y, the slope of the asymptote, and actually let me write this for you. So the asymptote is equal to r sub y divided by r sub x. That's the slope of the asymptote. And then to find the full equation of that line, you would include x minus h plus k. When you look at the equation that we have here, when you subtract things, order matters, because 8 minus 5 is different than 5 minus 8. When the x term is the lead, then your parabola is going to open left and right when x is out in front. On the other hand, if y is your lead term, if the y stuff is the lead term, then your parabola is going to open up and down. So if like y minus k divided by r sub y squared is the first term out in front of the subtraction, if you swap the order in which you do them, you will change the direction that the hyperbola opens up and down. The equation of a hyperbola that has a center at 2, 7, a focus at 7, 7, and a vertex at 5, 7 is, we're told that we have a center point at 2, 7. So let's draw that. We have a focal point at 7, 7. And then finally, we have a vertex at 5, 7. Remember, this vertex is sort of part of that shadow ellipse. It's not really there, but sometimes I like to draw it in because it helps you understand, that the vertex is part of that shadow ellipse. And then your hyperbola is actually going to branch off like this. The hyperbola starts at the vertex and it opens towards the focal point. And for everything that we draw to the right, there is a mirrored component to the left. Because remember, there's like an r sub x here. There's also an r sub x going this way. There's also an r sub y going up and an r sub y going down. But remember that r sub y is only part of the shadow ellipse. It's not part of the actual hyperbola. Do we know the location of the center? Yeah, that's 2, 7. Okay, great. Do we know r sub x? So in other words, what is the distance between the center and the vertex? Yeah, and you can get that by looking at the graph and subtracting the x coordinates. So 5 minus 2 is going to be 3. So r sub x equals 3. What about r sub y? And we don't have a direct way of doing r sub y because we don't have a coordinate for it. So in order to solve for r sub y, we have to make use of the focal point. The focal point is equal to the square root of r sub x squared plus r sub y squared. And do we know the focal length? The distance from the center to the focal point. And again, you do the same trick. You subtract the x coordinates and it's 5, right? So this becomes 5 equals the square root of r sub x, which we already said was 3, plus r sub y. So now we solve this. So I would square both sides, and then subtract 9 from both sides, and then square root both sides. 4 equals r sub y. So r sub y is equal to 4. So r sub x is equal to 3. R sub y is equal to 4. If we go back up to our formula, we can plug in values. So this a is r sub x, and so we'll put a 3 in for that. R sub y is b, and I know that because it's under the y term, so that means we have a 4 in there for b. C is going to be our h, which is the x-coordinate of our center point, so that's going to be a 2. And D is going to be 7. So this is a 2, this is a 7, this guy here is a 3, and this is a 4. H and K were pretty easy. That's the center point. They gave us that straight away. But we had to do a little bit of work to obtain r sub x, and even more work to obtain r sub y. Right? How can we make this more difficult? Yeah, I could not give you the information as straight up points. I could give you the information as an equation. Maybe something like this equation. And guess what we have to do with this equation? We've got to complete the square. And how many times do we have to complete the square? Not once, but twice. Don't cry.
Don't cry.
9x squared minus 54x. And then I'll put my y terms together. So I'll say minus 36y squared plus 144. And if it's all right with you, I'm going to take this negative 387 and just kick it over to the other side and make it positive 387. So now I'm going to take those x terms and I'm going to factor out a 9. And then for the y's, I'm going to factor out a negative 36. And that's going to leave me with y squared minus, be careful of the signs, right? You're factoring out a negative 36. 36 times y squared minus, what is that, 4y plus blank equals 387 plus the blue blank plus the green blank. What goes in the blue blank?
9.
Yeah, 9. Negative 6 divided by 2 squared. It's going to be a 9. But I'm not just adding 9, I'm actually adding 9 times 9, which is 81. So in the blue blank over here, I got to put an 81. What goes in the green blank? A 4. So negative 4 divided by 2 is negative 2. Square it, you get a 4. But I'm not adding just 4, I'm actually adding negative 36 times 4, which is negative 144. So this becomes 9 times x minus 3 squared minus 36 times y minus 2 squared equals, okay, so remember for an ellipse we need this guy to equal 1. So we're going to divide everything by 324, divide by 324, divide by 324. X minus 3 squared divided by 36 minus y minus 2 squared divided by 9 equals 1. It's a hyperbola because they're subtracted. If they were added, it would be an ellipse. Where's the center? So the center is at 3, 2. What is r sub x? 6. And what is r sub y? 3. So let's see. H is 3, k is 2. A is associated with the x stuff, so that's r sub x, so that's a 6. And B is associated with the y stuff, so that's a 3. Does this hyperbola open up, down, or does it open left, right? It opens left, right. And how do you know? Because the x is the first term. If y's were the first term, then it would open up, down. The 4 things that we've talked about in this chapter are called conic sections. And the reason they're called conic sections is because if you take a cone and you slice it with a plane, or basically you run a sheet of paper through it, you get these shapes. So if you take a cone and think of like one cone on top of the other, like they have here, one cone opens up, the other cone opens down. If you run that slicing sheet of paper through it So that way it goes through the side and it goes through the bottom. The cross-sectional area makes the shape of a parabola. If you run that slice through it horizontally, the cross-sectional area is a circle. If you run that slice through it at an angle, through both sides, you get an ellipse. And if you run it through vertically, you get the hyperbola. So this is like a three-dimensional understanding of what these shapes are. This is all three shapes on a single cone. So you can imagine a sheet going through horizontally, that gives you the circle. Another sheet going through like at an angle, that's the ellipse. A sheet going through the side and the bottom, that'll give you a parabola. And a sheet going through the bottom and then the bottom of the other side, that gives you the hyperbola. So this is a picture of a lamp in my living room. And if you take a look at the shadow and the light, what do you see? Yeah, it's a hyperbola. So the light bulb is probably right about here. That would be the center point, H and K. So there's a vertex there and there's a vertex here. And up here would be a focal point. And down here would also be a focal point. The light bulb is throwing out light rays in all directions. The light rays that go this way hit the side of the lampshade and are absorbed. They don't escape. But this light ray does escape. And this light ray escapes and goes that way. What are those? Those are your asymptotes. This guy here would be r sub x, and this guy from here to the vertex would be r sub y. So we could actually calculate the equation of that asymptote. So I actually took the picture, put it in GeoGebra, and then slapped a hyperbola on top of it, and that is the equation of the hyperbola for the lamp in my living room. So let's put an x-axis on this. Let's put a y-axis on it. Let's slap a grid on it. We can't really do like three-dimensional Oculus Rift stuff, but we could take a two-dimensional picture, slap it into GeoGebra, put an x-axis, a y-axis, and a grid on it, and come up with the equation of this. When your focal point is inside the directrix circle, you have an ellipse. When your focal point goes outside the directrix circle, you have a hyperbola. Ellipse, hyperbola. Ellipse, hyperbola. If the focal point is at the center, you have a circle. If the focal point is off of the center, in between the center and the directrix, you have an ellipse. If the focal point is on the directrix, you have a line, which I can't do very well. And if it's outside of the circle directrix, it's a hyperbola. Circle, ellipse, hyperbola. All because we took that directrix that was a line and we made a circle out of it. Here's the parabola. But this is a linear directrix. If you take that linear directrix and you change it to a circular directrix, you get this. Here's the circle. Here's the ellipse. Here's the line. That's the best I can do it. And there's the hyperbola. Most of the hyperbolas that you work with in the homework have a center at 0, 0. They're at the origin. So that means h equals 0 and k equals 0. On this one, it's pretty easy to find r sub x. That's just the distance from here to here, and that's going to be 2. But where's r sub y? Like we don't have a physical object up here to say, oh, the distance from here to here is r sub y. But we do have this asymptote. And remember, the slope of that asymptote is equal to r sub y over r sub x. So it looks like the slope of this guy is up 4 and to the right 2. So if you think about the slope being 4 over 2, that equals r sub y over r sub x. We know r sub x is already 2 because we counted that. R sub y equals 4. Use the slope of the asymptote in order to find r sub y. So if you want to take this further and find the focal point, it'd be the square root of r sub x squared, bless you, plus r sub y squared. When we talked about hyperbolas way back up in here, there were a couple new additions, and one was this idea of an asymptote right here.